Dr. R. Hemavati is an assistant professor in mathematics in Queen Mary's, Chennai. She has specialized on functional analysis. Having 12 years of experience in teaching, she has won various awards for her performance. She has published papers in 14 international journals, 3 national journals, and has presented papers in 10 international and in 5 national conferences. She is also one of the editors for an international journal.
Welcome to UGC lecture series. Earlier, we were studying some special continuous probability distributions like gamma distribution and beta distribution. In the previous session, we have seen beta distribution of first kind. In this session, you are going to study about beta distribution of second kind, which is also a continuous probability distribution. What all the contents you are going to see in this session is definition of beta distribution of second kind. Earlier we have seen beta distribution of first kind. As already discussed, based on beta function being represented in two formats, one is for a specified interval 0 to 1 and another is for infinite interval 0 to infinity. We have two distributions in beta, that is beta distribution of first kind and beta distribution of second kind. So, in this session we will go ahead with studying definition of beta distribution of second kind, and also we will derive the constants of beta distribution of second kind. Constant means mean and variance. We will also work out an example after assorting the distributions of gamma and beta. And also we will study statement of Chebyshev inequality. Next, beta distribution of second kind definition goes like a continuous random variable x is said to follow beta distribution of second kind with parameters m comma n, where m and n both are greater than 0 if its PDF is given by f of x equals to 1 by beta of m comma n x power m minus 1 by 1 plus x whole power m plus n, where m is given to be greater than 0, n is greater than 0, and you have the x interval 0 to infinity. Okay. It is equal to 0, the PDF is 0 otherwise. Okay. This is the PDF of beta distribution of second kind. Constants of beta distribution of second kind we will derive now using the moments formula. First of all, we will derive the rth moment of beta distribution of second kind, and using r is equal to 1 you will get mean, and using r is equal to 2 you will get mu 2 dash. From mu 2 dash we will derive the variance, which is mu 2. Mu 2 is mu 2 dash minus mu 1 dash square as usual. Okay. So, first of all we will derive mu r dash. Mu r dash is expectation of x power r. Since it is continuous distribution, it is integral x power r into f of x dx, and we will substitute the limits 0 to infinity x power r. The definition beta of 1 by beta of m comma n x power m minus 1 by 1 plus x whole power m plus n dx. Okay. So, this 1 by beta of m comma n is taken outside, integral 0 to infinity, club this x power m plus r minus 1 by 1 plus x whole power m plus n. So, how it is written in the format, here you are having the place of m you are having m plus dx, in the place of m you are having m plus r. So, here also it should be in the format of m plus r. So, what I will do here, I will add this r and minus r, it will not affect the power. So, therefore, you have 1 by beta of m comma n integral 0 to infinity, arranging it in that format, m plus r minus 1 by 1 plus x whole power m plus r plus n minus r dx. This is one of the beta integral where in the place of m you are having m plus r and in the place of n you are having n minus r. Okay. So, this is equals to 1 by beta of m comma n into beta of m plus r comma n minus r. Okay. Using the gamma function for the definition of beta function, what is that beta of m comma n in terms of gamma? Beta of m comma n is gamma m gamma n by gamma m plus n. This is the formula for beta of m comma n. So, here we have gamma of m plus r, gamma n minus r by gamma m plus r plus n minus r by gamma m, gamma n by gamma m plus n. Okay. And here this r gets cancelled. So, this is gamma of m plus n, gamma of m plus n and gamma of m plus n can be cancelled, and you have ultimately mu r dash equals to gamma m plus r, gamma n minus r by gamma m into gamma n. This is mu r dash. We will now write down what is mean. Mean is equal to mu 1 dash. You have to put r is equal to 1 in the mu r dash just derived. What is r is equal to 1? If you put, it is gamma of m plus 1, gamma n minus 1 by gamma m into gamma n. Now, we have to cancel and the gammas, so that you get a simplified format in the for mean. So, how to write? Gamma m plus 1 can be written as m gamma m, and gamma n minus 1 cannot be reduced. Even if it is reduced, it is not useful for cancelling. Therefore, I will reduce gamma n. Gamma m is written as it is, so that you can cancel, and gamma n is written as n minus 1 into gamma n minus 1. So, this gamma m gets cancelled and gamma n minus 1 gets cancelled, and you have only m by n minus 1. This is mean of beta distribution of second kind. Okay. Next, to find variance, which is mu 2, which is mu 2 dash minus mu 1 dash square, okay, where mu 2 dash is equal to is obtained by putting r is equal to 2 in the mu r dash formula. So, mu 2 dash is equal to gamma m plus 2 gamma n minus 2 by gamma m into gamma n, and gamma m plus 2 is written as m plus 1 into m into gamma m. Gamma n minus 2 need not be reduced, and gamma m is kept as it is, and this n gamma n is reduced as n minus 1 into n minus 2 into gamma n minus 2. So, now gamma m gets cancelled, gamma n minus 2 gets cancelled. You have only m plus 1 into m by n minus 1 into n minus 2. This is mu 2 dash. Okay. Therefore, variance is mu 2, that is mu 2 dash minus mu 1 dash square. So, m plus 1 into m by n minus 1 into n minus 2 minus m by n minus 1 whole square, and this gives you m into m plus n minus 1 by n minus 2 into n minus 1 whole square. So, this is the variance. Let me write it clearly. Variance is equal to m into m plus n minus 1 by n minus 2 into n minus 1 whole square. Hence, we have derived the constants of beta distribution of second kind. Mean is m divided by n minus 1, and variance is m into m plus n minus 1 by n minus 2 into n minus 1 whole square. Next, after we have studied this gamma distribution and beta distribution, let us see how they are related. We have seen gamma distribution, we have seen beta distribution of first kind, that is beta 1 of lambda 1 comma lambda 2. We have seen beta distribution of second kind, that is beta 2 of m comma n. Okay, we will see this example wherein if x1 and x2 are independent gamma variates with parameters lambda 1 and lambda 2 respectively, show that the variables u is equal to x1 plus x2 and v is equal to x1 divided by x1 plus x2 are independent, and u is following gamma variable with lambda 1 plus lambda 2 as a parameter, and v is a beta 1 distribution, that is beta distribution of first kind with parameters lambda 1 comma lambda 2. Let us see this and we will derive using the transformation of random variables. Transformation of random variables in two variables. We will see this. First of all, given x1 follows gamma distribution with parameter lambda 1. So, immediately we will write down its PDF. What is the PDF? F of x1, that is f1 of x1 is equal to 1 by gamma lambda 1 e power minus lambda 1 x power lambda 1 minus 1, and it is also given x2 is following a gamma distribution with parameter lambda 2. So, what is its PDF? f2 of x2 is equal to 1 by gamma lambda 2 e power minus lambda 2 x power, here it is x1, right. So, here it is x2 power lambda 2 minus 1. So, next given x1 and x2 are independent. So, using the independency property, we have the joint distribution f of x1 comma x2 is equal to f1 of x1 into f2 of x2. This is equal to 1 by gamma lambda 1 e power minus x1 power lambda 1 minus 1 into 1 by gamma lambda 2 e power minus x2 power lambda 2 minus 1. Then clubbing this and writing it in a format 1 by gamma lambda 1 gamma lambda 2 e power minus of x1 plus x2 x1 power lambda 1 minus 1 x2 power lambda 2 minus 1. This is the joint distribution of two random variables x1 and x2. Okay. Now, it is given u is equal to x1 plus x2 and v is equal to x1 divided by x1 plus x2. We have to obtain the inverse transformation. Inverse transformation is u is given in terms of x1 and x2 and v is given in terms of x1 and x2. Inverse transformation is you have to obtain x1 in terms of u and v and x2 in terms of u and v. Okay. So, what is it? U is x1 plus x2 and v is x1 by x1 plus x2. When you multiply, you get uv is equal to x1 plus x2 into x1 by x1 plus x2. So, cancelling, writing it in the reverse format, x1 is equal to uv, right, and x1 is equal to uv and u is equal to x1 plus x2. Substitute u is equal to uv plus x2 implies x2 is equal to u into 1 minus v. This is the inverse transformation. U is x1 plus x2, v is x1 by x1 plus x2. So, u, v are in terms of x1 and x2. Now, we have got the inverse transformation x1 in terms of u and v, x2 in terms of u and v. We have got the inverse transformation. Next, we will go ahead to find out the joint distribution of u and v, and then we will find out the marginal probability density function of u and then marginal density function of v, and we will prove that g of u comma v, that is joint distribution of u comma v, can be written as a product of their respective marginal PDFs. Marginal PDFs is g1 of u into g2 of v. Okay. So, we will prove this. First of all, for that you have a separate formula in transformation of two dimensional random variables, and then now I will write down all these things together. U is equal to x1 plus x2, v is equal to x1 by x1 plus x2, and then you have x1 is equal to uv, x2 is equal to u into 1 minus v. So, we have got x1 is equal to uv and x2 is equal to u into 1 minus v. Let us write all the things together. U is written as x1 plus x2, v is x1 by x1 plus x2, x1 is equal to uv, x2 is equal to u into 1 minus v, and all these things has to be dealt in terms of transformation of two dimensional random variables. Okay. Given 0 less than or equal to x1 less than or equal to infinity and 0 less than or equal to x2 less than or equal to infinity. This is based on x1 is following a gamma distribution and x2 is following a gamma distribution, right, and this implies u is equal to x1 plus x2, these two implies 0 less than or equal to u less than or equal to infinity, and v is equal to x1 by x1 plus x2, and writing it in the small case because the variables now we are writing its limits, therefore, you can write it in small case. Okay. This can be written as x1 by x1 into 1 plus x2 by x1, x1 gets cancelled. So, that as x1 tends to infinity, this becomes 0. So, 1 divided by 1 plus 0, and ultimately you have the limits as 0 to 1. So, therefore, 0 less than or equal to v less than or equal to 1. Okay. For 0 to infinity of x1 and 0 to infinity of x2, you have got the limits as 0 to infinity for u and 0 to 1 for v. Next, the Jacobian we have to find out. Jacobian for this transformation, Jacobian j is equal to modulus of dou x1 by dou u, dou x1 by dou v, dou x2 by dou u, and dou x2 by dou v. Okay. x1 is uv, x2 is u into 1 minus v. So, what is dou x1 by dou u? It is v. Dou x1 by dou v is equal to u, differentiating x1 partially with respect to u. With respect to u means v is considered as constant, therefore, v is kept as it is and differentiation of u is 1. So, 1 into v is v. Dou x1 by dou v, similarly u into 1. So, x2 is equal to u into 1 minus v. So, dou x2 by dou u is equal to 1 minus v, dou x2 by dou v is equal to minus u. Okay. Substituting all these things here, we get j is equal to v u 1 minus v minus u. Therefore, j you will be getting it as minus u. Now, joint distribution, joint PDF of u and v is g of u comma v is equal to f of x1 comma x2 into modulus of j. F of x1 comma x2 is 1 by gamma lambda 1 into gamma lambda 2 e power minus x1 plus x2, x1 power lambda 1 minus 1, x2 power lambda 2 minus 1 into minus u. Now, these x1 and x2 has to be changed in terms of u and v, because this is joint PDF of u and v. What is x1 plus x2? It is nothing but u. What is x1? x1 is uv power lambda 1 minus 1. What is x2? u into 1 minus v whole power lambda 2 minus 1. Since it is modulus, u comes outside as a plus u. So, clubbing all these powers, 1 by gamma lambda 1, gamma lambda 2, e power minus u, u power lambda 1 minus 1 plus lambda 2 minus 1 plus this one into v power lambda 1 minus 1, 1 minus v power lambda 2 minus 1. Minus 1 plus 1 gets cancelled, and you have ultimately 1 by gamma lambda 1, gamma lambda 2, e power minus u, u power lambda 1 plus lambda 2 minus 1, v power lambda 1 minus 1, 1 minus v power lambda 2 minus 1. Okay. Now, this is the joint PDF of u and v we have got. This has to be arranged in a format so that u follows a gamma distribution with parameter lambda 1 plus lambda 2 and v follows a beta distribution of first kind with parameters lambda 1 and lambda 2. You can arrange it. How this is arranged? That is 1 by gamma lambda 1 gamma lambda 2 by, before that we have to multiply and divide by gamma lambda 1 plus lambda 2. I am writing, I multiplied gamma lambda 1 plus lambda 2, I am writing it here. Okay. And e power minus u, u power lambda 1 plus lambda 2 minus 1. Okay. This is written here into v power lambda 1 minus 1, 1 minus v power lambda 2 minus 1. This multiplied gamma lambda 1 plus lambda 2, I am writing it here. So, divided lambda 1 plus gamma lambda 1 plus lambda 2 is written here. This gets cancelled, means you will get the usual joint PDF of u and v. Now, how to club this? This gives you beta of lambda 1 comma lambda 2, and this can be clubbed with that. What is that? V power lambda 1 minus 1, 1 minus v power lambda 2 minus 1. Okay. So, the remaining is this part, right. This part is e power minus u, u power lambda 1 plus lambda 2 minus 1 by gamma lambda 1 plus lambda 2. Now, we have got this is a beta 1 distribution of parameters lambda 1 lambda 2, that is v is following a beta, because this is in terms of v, right. So, v is following a beta distribution with parameter lambda 1 comma lambda 2, and now this is gamma variate with parameter lambda 1 plus lambda 2, that is here u, right, u is the variable here. So, u is a random variable following gamma distribution with parameter lambda 1 plus lambda 2. So, how this is written? This is g2 of v into g1 of u. Hence, we have got g of u comma v is equal to g1 of u into g2 of v. That is, the joint PDF of u and v is written as the product of two marginal PDFs, their respective marginal PDFs. G of u comma v is equal to g1 of u into g2 of v, wherein u is following a gamma distribution with parameter lambda 1 plus lambda 2, and v is following a beta 1 distribution. Beta 1 distribution means beta distribution of first kind with parameters lambda 1 lambda 2. Hence, we have arrived at this conclusion of the problem. Now, after studying the continuous distributions, based on the discussions in this session, this assignment problem can be easily solved. That is, if x1 and x2 are independent gamma variates with parameters lambda 1 and lambda 2 respectively, we can show that the variables u is equal to x1 plus x2 and v is equal to x1 by x2 are independent, and u is a gamma distribution variable with parameter lambda 1 plus lambda 2, and v is a beta distribution of second kind with parameter lambda 1 lambda 2. We can proceed similarly like the example done in this session, and you can arrive at g of u comma v is equal to g1 of u into g2 of v, where u is a gamma variate with parameter lambda 1 lambda 2, and you will get beta distribution. V is a beta distribution of second kind with parameters lambda 1 lambda 2. Proceed similarly like the example worked out in this session. We have seen several continuous distributions earlier and in these sessions. That is, we have seen a normal distribution, uniform distribution, exponential distribution, gamma distribution, and beta distributions of one is first kind and beta distribution of second kind. Hence, after studying these continuous distributions, we can go further to apply these distributions to some of the inequalities. In this session, we have studied beta distribution of second kind, we have studied the definition, and we have derived the mean and variance of a beta distribution of second kind. Also, we have worked out an example wherein we have used the transformation of two dimensional random variables, where the if x1 x2 are one is gamma variable and another one is beta variable. That is, if x1 and x2 are gamma variates, then using transformation you will get one variable u and as gamma variable of lambda 1 plus lambda 2, and v is beta distribution of first kind with parameters lambda 1 lambda 2. Thank you.